Good afternoon, and welcome for the first after-lunch talk of the conference. Who attended another talk on streams? It's, I think, data streams for fun and profit by David Ostrovsky earlier today. Yeah, if you are. David presented available providers of large streams of data, and he also showed what is available on JVM, on .NET, and gave us a little bit of classification. And when it came to .NET, he showed that there was only Orleans which was available. And it may have raised the question, okay, so if I want streams of data, can I use anything which is ready for me? And yes, you can. Because if you just don't rely only on streams provided by vendors, there is actually an initiative which lets stream almost any sequence of data, and it's available on multiple platforms, and it doesn't require you to know the low-level details of Akka model programming or Reactive Streams interfaces. So it might look like Akka Streams, it's a junction of two technologies, and it requires you to know more low-level details, but actually it's opposite. So we'll be talking about it. My name is Vagif, and I work for Norwegian company Miles. We are one of the sponsors of NDC conference, so if you're looking for a good place to work, then come to our stand and talk to us. Or if you're happy with your company but just want to grab some Italian food, you can also come to our stand and talk to us. So enough marketing pitch. Let's go to technical stuff. There are no prerequisites, technical prerequisites for this talk. You might be familiar with some of these, and that probably give you some, ring some bells for you, some common scenarios, but none of that is required to understand how Akka Streams work. And we'll spend probably like 15-20 minutes first to go through the motivation line, to explain how you can, not just how you can get to Akka Streams, but why. There was a blog post, which I think is from 2015, but I just recently read it, and it's explaining why it's so hard to explain monads to people. It's an everlasting story. Like, people try to explain monads, and people don't get it. And the author of this article, he said that one of the problems that we often get excited about things, and we forget that if you want to sell aspirin, we need to know that this other person, it knows what pain is. And you can't just explain what pain is, because if you have never experienced the pain, this cannot be explained. So if Akka Stream is aspirin, then what is the pain? So what can be the road to Akka Streams? And we'll try to identify a few ways towards Akka Streams. And first, this is actually my story of my last year and a half approximately. I've been doing Akka.NET development. And as for today, even though we're happy with results we're getting, I see that some of the things, some code could be written in a more compact way. And I can focus more on high-level abstractions if we used Akka Streams. Then, if you're familiar with Reactive Streams, Akka Streams gives you possibility to use them in practice without going through implementation of the interfaces. Then we'll be showing some Akka Streams building blocks. And this alone might be convincing for you to try how Akka Streams work. Finally, Akka Streams are built on so-called reactive extensions. We'll come to them later, which implement so-called back pressure, where publisher and consumer of data, they can dynamically agree about suitable data transfer rate. And this is a quite neat feature, and for many of us it can also be point of pain, because who can honestly tell how many messages your system is capable of tackling and what happens if it gets overloaded? So Akka Streams back pressure, it gives us opportunity to avoid that, to have contract of how many messages we get on each processing stage and what happens if buffer gets overloaded. So first road, it's from actors to Akka Stream. This is a slide from a presentation that me and my colleague Arlen Week we gave at another NDC conference in London this year, and we tried to explain other points of pain that led us to use actor model. Everyone who has been working with enterprise applications that require multiple threads and high availability know how hard it's to provide manual thread management, thread synchronization, and to manage shared state. So these three evil faces was, for us, one of several reasons why we decided to give Akka a try. And even though we are, in general, happy with our choice, but of course, every technology has its own limitations and obstacles, and there is a claim about actors that actors do not compose. This is one of the blog posts that, at least there is a lot of reference if you Google to this blog post, that since actors send messages to each other, then and actors when sending messages, they use addresses of inside Akka system. This is Akka system, and these are addresses. So we have an actor, and it sends messages. So it's sort of hard-coded. Of course, you can use dependency injection, but as actor model is defined, this is quite obscure. What happens? How messages are floating within actor system? Roland Kuhn, one of Akka architects, he disagreed with the original claim, but he tried to rephrase it, saying that what probably people mean when they say that actors do not compose. And since the only way to communicate with actors is to send a message, so basically you have a method, send message, which is void or unit. And in this respect, there is no composition between actors, because if you can't build a functional pipeline if functions do not return anything. So those who are familiar with functional programming know that this is pipeline operator, and it works very nicely. If you have function that returns something, you transform to next level, next chain, and you can't do this with actors. But then Kuhn added a comment to that, saying that actors do compose, actually, in the same sense as our human society composed. And you might think that this is kind of different context, so what social human society have to do with actor model. But if you think about how we people communicate, we communicate using messages, and we do compose great teams, great families, and those who attended Geek Beer yesterday, I mean, we composed a good beer party just by sending messages to each other. So this is the same way actors work. But still, from technical point of view, there is no composition which let us build functional pipelines using actors. Another thing is that often when you write actor code, you write quite tiny code. And then on the top of it, there is some boilerplate code. And it's okay if you have a large implementation, but if you have to write this code everywhere. In addition, you have similar code to arrange actors to have functions like pre-start, post-start, and so on. So it's quite a lot of boilerplate code. So you may get lost in a large code base, losing actual understanding of how communication goes. So what if we could still use actor model, but describe the data flow process differently, focusing on a high-level composition, like link. Here, everyone, of course, who does .NET, and even who doesn't, among developers, familiar with these link statements. So you can just chain using fluent syntax link statements. You don't need to write a class yourself that implements join or where. And this is a nice functional transformation. Like here, this is code in F#, and even those who are not familiar with F# actually can get a picture of what's going on here. We read the content of a web page, and then we extract words from it, and then we run spell checking control. So it's here we composed our flow, processing flow. Can we do something with actors? Actually, we can. So this is actually our first exposure to Akka Streams. Do you know what language it is written in? Scala, of course, Scala. So this is Akka Streams. You see, there is no code that manually creates any actors. What happens here is that we define some source. This is our stream source. And then there's a sink. We just ignore results. But we do some interesting stuff here. We define broadcast and merge. And then this is also code in Scala, by the way. So from source, we send data through flow. And flow just adds 10 to all numbers. Then we broadcast these numbers. And then on each next stage, we also add 10. Then we merge this data, and then again add 10, and then we send to sync. So it's very compact, actually very neat way using Scala to define streams. Probably for some developers it will be, after seeing this code, they can consider switching to Scala, because it really looks neat. If you look at C#, let's see. Yeah. So what this code shows us is that we can unlearn actually our ability to create individual actors. And instead, we can learn instead how to use high-level composition primitive. So we focus on our workflow. And our framework internally will create and connect all these instances of actors. And coming to C#, this is very simple, probably the simplest Akka stream in C#. We have a source, again enumerables, and then via some flow, we just multiply numbers by 2, and we write everything to console. And if you want to create something more complicated, and this is a graph DSL in C#. It's called also graph DSL like in Scala, but there is not much graphical here. Still, it's quite easy to understand what's going on here. It's just one page. You see that we add broadcast and merge. Then there are a couple of flows. So we actually create a counter, and with some counter, so we create a sum aggregate, even though Akka Stream has its built-in primitive for that. But this is just to show how you can do it in a different way. And then we merge data and return flow shape, which is a graph, which can be processed. So that's one way, one road to Akka Streams. If you have experience with Akka, writing actors individually, you can actually have alternative way of running your workflows. There is another road from Reactive Streams to Akka Streams. What is Reactive Streams? It's an initiative with several large companies behind that decided to provide a standard way for asynchronous stream processing. So they defined a minimal set of components and interfaces that stream provider must support. So these streams can be actually combined in a single processing workflow. And one important quality of such streams will be that support back pressure. Back pressure is, as I mentioned in the beginning, its ability to dynamically agree about message rate between a producer and consumer of the message. So there are a few original participators in this initiative, and Lightband used to be called TypeSafe at that time. And there are 4 components: publisher, subscriber, subscription, and processor that Reactive Streams specification requires. And there are 4 interfaces. Interfaces are very simple, and it might look like it's simple to implement them, because publisher just have 1 method, and subscriber has 4. Then we have subscription with request and cancel, and processor doesn't have its own method. It just derives from publisher and subscriber. But in fact, those interfaces are not meant to be used by client API. They are to be used by those who implement stream sources. So these interfaces, they let us to support very important feature which is called back pressure. What is it about? You may have a slow consumer of data. What happens if the stream uses push model and publisher just keeps pushing data on the subscriber? Well, then subscriber sooner or later will be overloaded with these messages. So push model doesn't really work for slow subscriber. But it's not efficient if we use pull model, and then the publisher will be slow. Because if subscriber just keeps on pulling data and there is nothing to get, then this communication will become inefficient. So what Reactive Streams specification enables is that publisher and subscriber, they can switch between pull and push model dynamically within a single session, depending on how fast communication goes. So this is an example of a test of back pressure on Apache Flink. Publisher and subscriber. Originally, publisher was slow. They just added thread sleep to publisher, and subscriber, of course, followed and received messages on a slow rate. Then they made subscriber slow. So it was capable only consuming about 20% of publisher speed. And publisher followed immediately. Then they removed all breaks and all data was consumed at high speed, then added slowness, again works fine, and then finally they removed, and publisher and consumer, they process data at the highest rate. So this is illustration of this dynamic push-pull agreement between publisher and subscriber. So Akka Streams building blocks, they include various sources, flows, and sinks. So a source is a processing stage with exactly one output. You can have multiple sources that give you data, but each source, it has no input, it just gives you the data. So this is originally where your stream starts. Then you have sink. It's where your data eventually come. It's a stage with just one input. And then you have flow. Flow, according to specification, has exactly one input and output, although developers often relate to flow as stage with at least one input and at least one output. Although, strictly speaking, it's not a flow, it's a graph. Because graph, it's a combination. It can consist of flows, sources, and sinks. And not every graph is runnable. Only closed shape is runnable, which means that if you have a graph with open ends, you can't run it. So you have some sources, you have to stream the data somewhere, and then eventually data must come to the sink. Then you have a runnable graph. If you look at built-in source stages for Akka Streams, there are plenty of them, and I'm now showing you Akka.NET implementation. For Scala, it's different, although there is a lot of similarities, but some of these are just for Akka.NET. For example, this from enumerator. If you have enumerator, you can get a stream out of it. From gives you from any enumerable. So actually, if you have any sequence of data, anything that gives you enumerable, you can make a stream out of it, Akka stream. Here are built-in sync stages. From ignore to some aggregates, like aggregate and sum. And of course, you can just stream data right to files, or you can send them to some actors. So there is a lot of possibilities. And even bigger number of built-in flow stages. And it looks like link statement or link expression types in a way. I think there are probably 83 link expression types, and there's a comparable number of built-in flow stages. So once you get data, you can do various things with them, like map reduce, filtering, buffering, throttling, all this available no matter what is your stream source. So this makes it attractive, even if you not familiar with Akka or Reactive Streams. You can just start from scratch, basically get some enumerable as a stream, and then start processing it. Stream needs to be materialized. So the actual stream specification that we saw, it can't be run without Akka system. So we just declare a stream, and like a link statement, if you have a link statement with some link providers, they have so-called deferred query execution, which means that if you don't have this toList, and this is a link statement that you use with SQL Server, you don't get any data until you materialize them. And materialization is just to call toList, to array, single, first to default, anything that actually require actual data retrieval. The same is with streams. This is just a blueprint. So it's a specification of how streams should work. And in order for this stream to work, you should create an actor system. And this is as easy as just calling actor system create. So you don't really need to have a knowledge of how actor system works. And then you create materializer, which is a disposable object. You can materialize stream multiple times, and probably will get different data if it's a really live stream. And then, as long as you have a runnable graph, you can just call run, and you will start getting data. Then, stream can produce materialized values. If you think about stream processing stages, you have source, you have some flows, you have sink. On each stage, data are coming and leaving the stage. And if you don't retrieve them, if you don't specify that you want to get hold of them, they're not used. And so here, for this stream, we're getting a runnable graph of not used, which means that we have a stream, we can run it, but it doesn't produce any materialized value, even though it actually, in the sink, it actually populates the list. But this comes as just as a side effect. Alternative is to run stream to materialized. So you want to produce some materialized value of some of the running stages. So here we have a sink where we have some integers, and we can say that we want to have a right part of this processing stage to be materialized. So we want to get this data. So then we're getting not runnable of not used, we get runnable of task of int. And we can retrieve materialized values from multiple stages, and then here we will have some tuple, tuple of values. So this is a very convenient way of just taking care of intermediate data without going to infrastructure level. So how do you consume Akka Streams? What do you need to do to start consuming them? Of course, as we saw, the built-in sources, built-in source stages, they provide a wide range of streaming data. And the easiest is just to use from enumerator or from input stream, from file. If you're using Akka and you're using persistence actors, then you can use Akka persistence query. It's a module that lets you stream data from event database of actors. So you get either live or snapshot stream of it, or historical stream. And then there is open source initiative which is called Alpaca connectors, both on Scala and .NET. And like with David's talk, who showed plenty of implementation for JVM and just one for .NET, here the major of connectors, they are for JVM. So this is just extract from the list. You get much more. You have Kafka, you have MQP, and so on, HBase. When it comes to .NET, the list is currently quite modest. It's Azure, you have storage queues, Event Hub, and Service Bus, and you have SignalR, and MQP is in work. And this is actually quite fresh tweet. It was about 10 days ago. David Fowler, he said that now SignalR is friend with Reactive extension, and Bartosz, he's one of key contributors to Akka.NET. He said that, by the way, we had this connector SignalR for a while. So if you're using SignalR, you have a stream for that now. So now we have gone through some definitions of what streams are, how they work. Then let's go through some cases. We'll go through a couple of some small case studies. First is actually how I was exposed to Akka Streams in our project, Streaming Event Journal, and then later we look at how we can stream tweets So everyone who is working with streams create examples with reactive streams, like streaming a tweet. That's probably the most common ground for all developers. So streaming event journal. So this is a dashboard that we have in our project, and it's actually it's a dashboard that is dynamically changing all the time. So it shows, we distribute some files, and it shows the status of files that we're distributing. It's a Kibana dashboard, and it's based on Elasticsearch index. And it shows data that's populated based on some actors that we have, persistent actors. So this is activity dashboard, and these are principles that we use to build it. Elasticsearch, Kibana. Who is using Elasticsearch? Yeah, more than half, I think. And index, like with Elasticsearch indexes, it's recommended that you don't use them as your primary source of data. You just create index, and we create them on demand. Typically, when we change the model, the layout of data that we want to show, that this is an ongoing project, so it's changing. And our persistent actors are stored in event journal, which is based on SQL Server. And this is the table. And we don't have a control over this table. It's Akka. This is event journal table. But we need to, in order to build our dashboards, we need to create indexer that first gets historical data from event journal, from SQL Server, and on the top of it will run the live event that our persistent actors receive. So we started thinking with my colleague, Pavel Banka, about how we should build it. And then whatever solution we came with, we were not really happy, because you have this relatively small piece of code that we don't really need to solve our domain tasks. And then we need to do something to grab data from SQL Server, and then we need to synchronize it. So we start from where it ends. We start with live events. So we're not happy with what we were getting until it struck us that we could use just Akka Streams, because Akka provides persistent query. And there are 6 predefined persistent queries, and this is what we needed. So it's events by tag and current events by tag. All which starts with current is just a snapshot from the beginning of time until now. All that doesn't have current, it's a live events, but you can actually get them from the beginning of time. So it starts from the first event ever received by actors, and then it continues streaming all events, and then just fluently goes into live events. So this was exactly what we needed. We didn't really need to build this hybrid component that takes things from SQL Server and then combine them with live events. And this is a resulting code. And you can recognize probably already that this is something about Akka Streams. It's written in F#, but it's very similar how we would have written in C#, because this part is common more or less. So we have events by tag, and we apply certain flows to that. And then we send the result to Elasticsearch. So this is example of once you get hold of stream of data, how easily you can use it to produce things like dashboards in this case, and how little code it requires you to write because of these primitives that are available to you. And now something that probably more usable for everyone. It's how we can stream tweets. It's reactive tweets. It's a sample that's written both for Akka Scala and Akka.NET. And I have written my own based on the same library, which Akka.NET uses. Scala uses different, but Akka.NET using open source library called TweetNV. So this library provides several streams. I didn't want to filter anything. I just wanted to get sample streams. So I will be using sample stream. And to Tweet NV doesn't support reactive stream specification, which means it doesn't support back pressure. And you have to do something to convert it into reactive streams based streams. But that's very easy, thanks to a lot of available primitives in Akka Streams. So what we're going to build, we will start with very simple workflow, but then eventually we will have a broadcast. So these are tweet sources. We'll run them through broadcast. On the first channel, we just format them and send to merge. On the second channel, we will throttle them because we are going to send them to weather forecast service, and if we send too many of them, then they can ban us. And so we get back results, and then we format results, and then we merge everything, and then write to the console. So let's see how this can be achieved. So I'm switching to Visual Studio. OK, and yes, I need to follow it on this monitor. So first this is a program, and here we have use cache tweets false. So first we will try with live tweets, but with live tweets we don't get them at very high rate, and also usually most of them don't have locations, but I want to play with locations, so I will switch to cached tweets. So first is just to demonstrate that we can get live tweets from Twitter. So let's see how it works. So if I go to utils, yeah. So this is a method to get our live tweets, start tweet stream. So this is Tweet NV API, create sample stream, and then we register some event receiver. So what we do with it, like, okay, here is the Akka stream that we define, source, flow, and sink. So what we do, we create an actor, and we send live tweets to this actor. Then we create a flow where we format this tweet, and we send to sink that just writes everything to the console. So if we run this program, shift, yeah. So here we're getting a live stream of tweets from Twitter. That was simple, but it doesn't show us really advantages of Akka Streams. So now let's go back to program. Okay, I have a hard time seeing it in this. Yeah. Now we set use cache tweets to true. And the first thing which we try, we just try cache tweets. And here the difference, if you compare, okay, cache tweets, here it is. If you compare with how we get live tweets. With live tweets, we created it from actor, but here we already have a file with cached tweets, so we just create cached tweets from enumerator. Very little difference. And if you run this program, okay, yeah. We're getting tweets on a much higher rate because this is just contents of the file. But all the format is the same. So now what we are going to do next is we try to, let me see, tweets with broadcast. So now we'll start broadcasting them. And this is how our graph will look. So here is something more interesting. We have a tweet source, the same source, and then we sending data to two channels. First channel is tweets will be formatted and only user name will be written. The second channel, we will just show only tweet coordinates. Then we merge both channels and we send them to the sink. So if we do this, if you run this program, yeah, you see we're getting 2 channels and at the same rate. Just name of the user and coordinates where he was tweeting from. So we're getting more interesting results now. So next thing which we're going to try is we have tweets with throttle. Let's see how this is implemented. Tweet with throttle. Yeah. So here we have a broadcast with 2 channels, and then we start throttling them. So let's try to throttle them first without using buffer here. So we're throttling at the same rate, like we're sending 10 messages a second, and see what happens then. Yeah, you see we're getting these tweets and they're written at the same rate. So now let's change this, and instead of having 10 messages per second for the coordinates channel, we'll just use 1 message a second. Okay, where is my coordinates? Yeah, it's here. So what do you think will happen? So now we request tweets at the rate 1 message a second on 1 channel and 10 messages a second on the second channel. Will they get messages at different rates, or they will get both at first 1 message a second or both at 10 messages a second? Who think they will be getting messages at different rates? Yeah, very few. That they will get messages at the lowest rate. Bit more hands, and they will be getting messages at the highest rate. Nobody. Actually, they will be getting messages at the lowest rate, as we can probably demonstrate now. Sorry? Sorry? Let me see. Okay. Yeah, I'm on the 3rd one. Yeah. So it's wrong if I'm getting with throttle. Yeah. This is the with throttle, and then I have we are 10, and then we want to have 1 here and 10 there. Let's try again. Thank you. Yeah. So now this is, it looks like it is. So you have only just 1 message a second. And why is that? Because we have a source, stream source, we have a broadcast, and then there is a request 1 message a second and the request 10 messages a second. But the stream source is just 1. It's a single stream source. So it can't start producing messages at different rates. So what it does, of course, it satisfies the lowest requirement. And this is how it works. So back pressure from flows, the strongest requirement will be satisfied. But this is not what we want. So what can we do? We go back to this file, and we're introducing a buffer. So here what we say, we want to buffer up to 10 elements. And if we let's have it here 1, since we have buffer here, and here 10. Yeah. So we want to buffer up to 10 elements, and after that, we will just dropping data that overflow the buffer. Yeah. So now we're getting 1 tweet, 1 coordinate a second, and 10 coordinate a second. 10 names a second. So now we see that these different flows they receive data at different rates. Why can this be useful for in our case? We want to send these coordinates to weather service, and then we don't want to be banned. So if we look now at the last file, which I mistakenly took for previous time. So here it is. Yes. So we have just users here created by, and here are the channels that get tweets, and we have buffer and throttle, and this throttle data we're sending to weather service. So here we use select async. So this is one of Akka primitives. Akka has both select and select async, and in Scala it's called map async. So we can just map asynchronously our data to some external service. And this is by the way, it's a parallelism. So we want to do it in parallel, up to 5 connections. So if you run it now, then we should be able to no, it's not. It's. I think I didn't change the in the program. Yeah, I didn't change the what runnable graph I want to use. Weather. Okay. Yeah. So you see, in the beginning, actually, it was buffering something. So we saw more weather forecast in the beginning. But now we see names, and approximately for every 10th name, we get coordinates. Oh, sorry, we get weather. Coordinates sent to weather service that returns back the weather. So to summarize what we have seen and the examples we have gone through with Akka Streams, I first thought about writing some bullet lists of takeaways, but then I thought that it's better probably to have some final thoughts on more conceptual level, because the Akka Streams started developing approximately the time where we first heard about serverless. And those two technologies that are not comparable technically, of course, serverless is much more spread. Akka Streams and Streams in general, it's a much more narrow than serverless. But like with serverless, we go from server-bound computation towards setting up environment where we don't care which service will be used to run our domain communication, run our business workflow. So, of course, it will be run on some service, and probably on the bigger number of servers than if we configured everything manually. But we sort of don't care. And this is a conscious choice which let us focus more on solving domain-specific tasks. The same way, those of us who had experience with Akka, we were focused on actor-bound computation. Like we were creating actors, we were carefully designing communication between actors. Instead, just like with link statements, we run this, we create, using GraphDSL, the graphs that show declaration of what we're going to compute. We define sources, flows, and sinks, and Akka Streams using stream materialization let us achieve same results with the same performance, but in much more code compact way, and shifting our focus to our domain-specific task rather than focusing on infrastructure, on plumbing. So this is what probably sort of the main takeaway which I would like you to take from this session. And this, how much time we have? yeah, we have some time. So this completes my technical part of session, but I often complete them with something which is not technical. And I'm going to present you musical interpretation of what I just said, which is called Akka Stream Wrap, where we're going to go through some Akka Streams primitives, which will make it easier for you to use Akka Streams in practice. So if audio works, let's, and you can sing along, of course. This is the Akka stream, and this is the source that feeds the Akka stream. This is the map async that maps from the source that feeds the Akka stream. This is broadcast that forks map async that maps from the source that feeds the Akka stream. This is the merge that collects from broadcast that forks map async that maps from the source that feeds the Akka stream. This is filter node that selects from the merge that collects from broadcast that forks map async that maps from the source that feeds the Akka stream. This is the balance that splits filter node that selects from the merge that collects from broadcast that forks map async that maps from the source that feeds the Akka stream. This is the tip that combines from the balance that splits filter node that selects from the merge that collects from broadcast that forks map async that maps from the source that feeds the Akka stream. This is the drop that removes from the zip that combines from the balance that splits filter node that selects from the merge that collects from broadcast that forks map async that maps from the source that feeds the Akka stream. This is the while that pulls from the drop that removes from the zip that combines from the balance that splits filter node that selects from the merge that collects from broadcast that forks map async that maps from the source that feeds the Akka stream. This is the throttle that speeds down the while that pulls from the drop that removes from the zip that combines from the balance that splits filter node that selects from the merge that collects from broadcast that forks map async that maps from the source that feeds the Akka stream. This is the flow that turns back the throttle, that speeds down the while, that pulls from the drop, that removes from the zip, that combines from the balance, that splits filter node, that selects from the merge, that collects from broadcast, that forks map async that maps from the source that feeds the Akka stream. This is the thing that is filled from BD flow, that turns back the throttle, that speeds down the while, that pulls from the drop, that removes from the zip, that combines from the balance, that splits filter node, that selects from the merge, that collects from broadcast, that forks map async, that maps from the source, that feeds the Akka stream. Thank you. Enjoy the rest of the conference, and I think we still have a few more minutes. So if you have any questions, that I'm here. Questions? Yeah.
So when you're defining actors normally in a supervision strategy, you define kind of how you want to handle failure. How do you deal with that when you're defining streams and graphs?
Yeah, you can. I didn't go in these details, but you with streams you have difference between error and failure. Of course, when stream fails, it's like it's done. That's it. But individual elements may fail. It's just an error, and you can still continue processing. And yes, you can. Of course, that will be more code to write, but you can back up with supervision strategies that provides like individual handling on each processing stage. More questions?
It actually works with the remote Akka actors.
Good question, and I didn't mention in my talk. For the time being, there is no distributed materialization for Akka Streams. That means that the stream declaration will be run on the same node. Of course, you can call external services. You can run it in the cluster environment. So different stream instances may be run in different cluster nodes, but you can't split processing stages between different nodes. So it's only local scenario for the time being. And it looks like for some time, because I saw discussion on forums, and then people from Scala Akka, some contributors, they said that it's not going to be prioritized in foreseeable future. And probably it means that it won't appear on Akka.NET too. More questions? Okay, thank you.